my computer.
You got it.
I see a
Yay.
little I see a little blinking red light. Says I'm sharing. Guess we're good to go. So here we go. Some definitions that we'll talk about. And basically propagation, kind of the formal definition, the way radio waves travel through space and material. Uh, you also could say it's just how they move from point A to point B. Uh, the propagation is affected by things like reflections, refraction, scattering, diffraction, and absorption. And we'll talk a little bit about all of those. The other one is radiation, which is actually not, you think of nuclear, this is just radiation of radio waves. And it's essentially how energy is transferred into electrostatic and electromagnetic waves and travels. We'll talk about the ionosphere, which is the basis for most of long distance propagation. And it's really the material in the Earth's atmosphere, the oxygen and nitrogen and other gases and particles that are in the upper atmosphere that are affected by solar radiation, X-rays, gamma rays, ultraviolet rays, and those all have enough energy to energize atoms and create free electrons, which causes the ionosphere to have positive and negative charges, or ions. And those interact with electromagnetic waves, and we'll talk about kind of how that happens. The ionosphere starts around 60 kilometers. It goes up to maybe 1,000. It really depends on the atmosphere itself. When there are no more atoms or molecules of the atmosphere for the sun rays to interact with, then there's no more ionosphere. And likewise, as you get closer and closer to the surface of the Earth, the atmosphere is denser. There's more molecules or atoms per cubic centimeter. And part of that effect is there's more energy, but there's also less solar energy making it down through those layers. So you have the highest ionization effect out at the top fringe where there's not a lot of molecules, and you have the least amount of effect down at the bottom where it's the most dense, down around 60 kilometers. And we call that the beginning of the D layer, and we'll talk about those layers sort of in the last section. Below that is the troposphere, which isn't really affected by solar radiation. It just doesn't make it down that far. It's kind of like, think of the ocean, sunlight going down, and at a certain point, it's just dark. It doesn't, the rays don't make it down there. We talk about ions, which are just atoms or molecules that really have a positive or negative charge because they've either lost an electron or they picked up an electron. Sunspots are one of the ways we measure solar activity, and those are dark, cool spots on the surface of the sun that tend to release more energy in those spots, particularly magnetic energy. And some of that can be solar flares or just magnetic energy that makes it to Earth. And we call those, depending on how dense it is, geomagnetic storms, because it interacts with the magnetic field of the Earth. The corona uh, is what they call the outer atmosphere of the sun, and that's where you see the flares. You see those, maybe you see those pictures of the sun, kind of like an orange ball, and you'll see like flames shooting out of it. Those are solar flares. And I mentioned geomagnetic, that refers to the Earth's magnetic field. Any questions on those? Okay. So first we'll talk about sunspots and solar radiation, some ionospheric disturbances, and some tools that are used for forecasting propagation. But first, if this works, we'll watch a movie. Is everybody seeing this?
Oh, no,
We're seeing the slide, but not the film.
Oh, well, I didn't start it. How about now?
And welcome to this presentation.
we see a slide that says HF propagation.
Okay. Did you hear it start?
No,
Wonder if I have to share that separate.
we see that yours cursor sitting right on the P in the middle of propagation. It's just static.
Oh, really?
I don't even hear static.
No, I
Okay.
don't mean static noise. It's just sitting there. The cursor's
oh.
sitting on the P.
All right. Let me see if I can share it. If I can find it. Okay. How about now?
Here we are.
In this presentation, we'll introduce you to the basic concept of HF propagation.
Turn it up. Yeah.
Did you hear it?
It's
Barely.
too quiet. It's too quiet. Need more
Oh.
volume.
It's up all the way.
Don't hear it. Do not hear it.
Well, I stopped
It's
it.
been playing, yeah.
Propagation and explain how HF propagation is influenced.
Yeah, we can't hear that.
We can hear murmuring in the background.
Okay, say that again.
We just hear a little murmuring. We can't understand it.
You can tell that it's playing, but you can't understand what it's saying.
Hmm.
So I don't know if you're going to need to turn your speakers up or maybe put your mic towards it or.
Oh, that's probably the problem.
Isn't it feeding straight out into us? I guess not.
That doesn't help.
You might try clicking on those three dots that are perpendicular on the bottom right there where the sound bar, and just see if it gives you an option. Nope.
No.
Well, as a thought.
Well, I upped the master.
and is usually used to refer to frequencies in the range of 3 megahertz to 30 megahertz.
Yeah, you might have to put your mic by the speaker, if that might help.
Well, all right. Let me.
So in many cases, the practical definition of HF can be extended down as low as 1.5 megahertz.
Well, that didn't seem to work.
Well, I went on Google and it says that once you share the meeting in your controls toolbar, in the right panel, select share sound checkbox, and that should help. The share sound option to view audio options and switch between mono and stereo. And in the bottom right, click share with your device's audio.
I'm not seeing audio sharing though.
Oh, bummer. Let's
Where?
see. Keep looking.
Back in the meeting, back in your slideshow? Is that what you're talking about, Donna?
Well, it says if you choose, let me go back up here at the top. It says start or join your Zoom meeting. In the meetings control toolbar, click share. In the right panel, select the share sound checkbox. And then you select the screen you want to share and then share, and it should do the audio. But another comment was that select the down arrow just to the right of the share sound option to view any options, and you can switch between mono and stereo, which helps.
This is back in the meeting.
In the
And
Zoom
share it.
program. The Zoom
Yeah, right
program.
now
Yeah.
it needs to be back in the slideshow, right?
In the
To see
Zoom
that.
program.
In the Zoom program, where you go to share the screen, there's an option to share the audio. You have to check that box. At
What
least
we're
that's
seeing
what
right now is a separate, are we in the slideshow, Bob?
Oh, here we go. Maybe.
This corresponds to wavelengths in the range of about 100.
Did
That
that
did it.
work?
I did it.
All right. Well, at least now we know.
Yep. Learn something
All right.
every day.
All right, here we
Thank
go.
you for your research.
Hello, and welcome to this presentation, Understanding HF Propagation. In this presentation, we'll introduce you to the basic concepts of HF propagation and explain how HF propagation is influenced by solar activity. HF stands for high frequency and is usually used to refer to frequencies in the range of 3 MHz to 30 MHz, although in many cases the practical definition of HF can be extended down as low as 1.5 MHz. This corresponds to wavelengths in the range of about 100 meters to about 10 meters. You'll sometimes also hear HF referred to, albeit somewhat imprecisely, as shortwave. The primary use of HF is for long-distance or even global communications. Broadcasters can reach listeners around the world using HF, and this global reach is also useful in many government and military applications. Amateur radio operators around the world also frequently use and experiment with HF. And as we'll see in this presentation, it's the unique properties of HF propagation that enable long-range communications or even global communications. Although propagation at HF can provide worldwide communications, HF propagation can also be highly variable compared to communications at other frequencies, such as at VHF and higher. As a practical matter, this means that the greatest challenge in HF is finding the optimum frequency for communicating with an intended destination under the current propagation conditions. Before we go into more detail about how this is done, let's briefly cover the three main HF propagation modes: line of sight, ground wave, and skywave. Line of sight is fairly easy to understand. Signals propagate in a straight, unobstructed path between the transmitter and the receiver. Line of sight is the only HF propagation mode which is fairly constant. Your ability to use line of sight to communicate with another station at a given location doesn't change much over periods of minutes, hours, days, months, years, etc. That said, HF isn't a very good choice for line of sight communications, and it's rarely used for this purpose. Because of the lower frequencies, HF requires large antennas, and bandwidth is also somewhat limited. There also tends to be much more noise at HF compared to higher frequencies. This can be a problem because the limited bandwidth at HF usually means communications are carried out over AM or single sideband, which are much more sensitive to noise than wider bandwidth FM. For these reasons, most line-of-sight communications are carried out at VHF or higher, not at HF. If we don't have a direct line of sight to another station, ground wave is a possible solution. Ground wave, sometimes called surface wave, involves signals propagating along the surface of the Earth. Interaction between the lower part of the transmitted wavefront and the Earth's surface causes the wave to tilt forward, allowing the signal to follow the curvature of the Earth, sometimes well beyond line of sight. Ground wave propagation is, however, highly dependent on two different factors: the conductivity of the surface and the frequency of the transmitted signal. In general, higher surface conductivity gives better results in the form of greater distances that can be covered. Salt water has excellent conductivity, especially compared to dry or rocky land, so ground wave is a good choice for ship-to-ship or ship-to-shore communications. With regards to frequency, ground wave works best for lower frequencies. For example, the theoretical range of a 150-watt transmitter at 7 MHz is 35 kilometers over land and close to 250 kilometers over the sea. At 30 MHz, however, our range falls to only 13 kilometers over land and just over 100 kilometers at sea. One of the most important propagation modes of HF is skywave, because it's skywave propagation that enables beyond line of sight or worldwide communications. In skywave, layers of ionized particles in the upper atmosphere refract HF signals back towards the Earth, allowing communications over many thousands of kilometers. The distances that can be covered by different frequencies are almost entirely a function of the state of these layers of ionized particles, collectively referred to as the ionosphere. In this presentation, we'll explain the different layers of the ionosphere, how the ionosphere is affected by the Sun, and how we can both quantify the current state of the ionosphere and predict the future state of the ionosphere. The incident angle, or the angle at which a signal reaches the ionosphere, also plays an important role in how far a skywave signal will propagate. The radiation angle of an antenna is primarily a function both of the type of antenna and the location at which the antenna is installed. Higher placement of an antenna usually lowers the radiation and incident angles. And generally speaking, the lower the incident angle, the greater the distance that is covered by skywave propagation. Note, however, that so-called skip zones may be created depending on radiation or incident angle. In these zones, HF signals can't be received either via skywave or via ground wave propagation. In order to understand skywave propagation, we should start by explaining how ionization occurs in the Earth's atmosphere. When ultraviolet energy or radiation from the Sun strikes gas atoms or molecules in the atmosphere, this energy can cause electrons to become detached. The result is a positive ion and, more importantly, a free electron. The Earth's magnetic field keeps these free electrons roughly in place. The level of ionization and the number of free electrons increases as the amount of sunlight striking a given part of the atmosphere increases. When that part of the atmosphere rotates away from the sun, that is, at night, the energy is removed and the ions recombine to form electrically neutral atoms or molecules. Note that recombination is a slower process than ionization. Atmospheric ionization increases rapidly at dawn, but decreases less rapidly after dark. As mentioned earlier, the region of the Earth's atmosphere that undergoes this ionization is collectively called the ionosphere. The level or density of ionization in the ionosphere is different at different altitudes, and areas with ionization peaks are often grouped into so-called layers or regions. The layers that are important for HF propagation are the D layer from 60 to 100 kilometers, the E layer from 100 to 125 kilometers, and the F layer or layers from about 200 to 275 kilometers. Note that these are only rough numbers. The thickness and altitude of ionospheric layers is never constant. The reason for defining these different layers is that each of these layers will refract and or absorb HF signals in different ways. It's important to note that the ionosphere does not reflect signals, but rather refracts signals. The different electron densities at different altitudes is what makes this refraction possible. Let's start with the lowest level of the ionosphere, the D layer. The D layer only exists during daytime hours and disappears at night. Although the D layer is ionized by solar radiation, the density of free electrons in the D layer is too low to effectively refract HF signals, and therefore the D layer cannot be used for skywave propagation. Instead, the D layer acts as an absorber of HF signals. This absorption is higher for lower frequency signals than for higher frequency signals. Absorption also increases with increasing ionization, so absorption is usually highest at midday. For these reasons, the properties of D-layer absorption mean that higher frequency HF signals work better during the daytime, whereas lower frequency signals work better at night, after this layer has disappeared. The next highest layer, the E layer, is the lowest layer of the ionosphere that can refract HF signals back towards the Earth, and is the lowest layer that supports skywave propagation. Compared to the other layers, it's relatively thin, usually around 10 kilometers or so. The E layer is much more dense, that is, ionized, during the day, but unlike the D layer, it doesn't completely disappear at night. Aside from mostly short-range daytime communications and a few other special cases, E-layer propagation is not commonly found in HF. Note, however, that at VHF, the E-layer is very important and supports some rather exotic and less predictable propagation modes, such as sporadic E, that make long-distance communication over thousands of kilometers possible, even at the relatively high frequencies of VHF. The F layer is the most important for skywave propagation. During the day, the F layer splits into two sublayers, F1 and F2, which merge back into a single layer again at night. Compared to the D and E layers, the height of the F layers changes considerably based on things such as time of day, season, and solar conditions. More on this shortly. The lower F1 layer primarily supports short to medium distance communications during daylight hours. The F2 layer, on the other hand, is present more or less around the clock. It has the highest altitude and the highest ionization of all the layers, and therefore is responsible for the vast majority of long-distance HF communications. The degree to which the different layers of the ionosphere refract and or absorb radio frequency signals is largely a function of that signal's frequency. The general rule for HF skywave communications is to always use the highest possible frequency that will reach a given station or destination. This is called the maximum usable frequency, or MUF. Signals whose frequencies are higher than the MUF will not be refracted by the ionosphere. Usually, the MUF increases with increasing ionization. Another important frequency threshold is something called the lowest usable frequency, or LUF. When the signal frequency is at or below the LUF, communication becomes difficult or impossible due to signal loss or attenuation. So we want to choose a frequency that's somewhere between the LUF and the MUF. There is one very important difference, though, between MUF and LUF. Because the LUF is mostly determined by noise, using higher transmit powers, a better antenna, etc., can improve or lower the LUF. MUF, on the other hand, is entirely a function of the ionosphere. You can't improve or increase the MUF by using more power or a better antenna. The MUF simply is what it is. And as we'll see shortly, if the LUF becomes greater than the MUF, no HF communication is possible. One way to determine the MUF is purely through experimentation, but there are also methods for estimating the MUF using something called the critical frequency. The process for measuring the critical frequency is as follows. Pulses at various frequencies are transmitted vertically by equipment called ionosondes. Depending on the frequency of the pulse, these pulses are returned by different layers of the ionosphere, and we can use the return time to estimate the heights of the different layers. Once we reach a certain frequency, the pulses are not returned by the ionosphere, and instead continue on into space. This is the critical frequency. Critical frequency is a function of both the current ionization level as well as the measurement location. It's measured regularly at hundreds of locations around the world. Mathematically speaking, the maximum usable frequency is the critical frequency divided by the cosine of the angle of incidence. If we send a signal straight up at 90 degrees, MUF and critical frequency are the same. But as a practical matter, the maximum usable frequency is usually estimated at 3 to 5 times the critical frequency. Critical frequency is one way of quantifying the state of the ionosphere, but it is an active test. We transmit signals and measure the return signals. In addition to critical frequency, there are 3 common passive methods that can be used to quantify the state of the ionosphere. The first of these is sunspot number, which can be used to predict the level of atmospheric ionization. The second is the solar flux index, which is an actual measurement of ionization. There are also 2 geomagnetic indices, the A index and the K index, which give an indication of the impact of solar particles on the Earth's magnetic field. Taken together, these quantities provide a good indication of the current state of the ionosphere and can be used to predict HF propagation. Let's take a look at each of these 3 quantities in a bit more detail. Sunspots are, relatively, cooler surface regions of the Sun. Relatively in this case means they have temperatures of about 3000 Kelvin versus the normal 6000 Kelvin seen elsewhere. After they appear, sunspots last between a few days and a few months. Sunspots are associated with powerful magnetic fields, and these fields affect how much radiation is given off by the Sun. The greater the number of sunspots, the higher the level of solar activity and radiation. And because of this, more sunspots generally means higher atmospheric ionization, a higher MUF, and better overall HF propagation. The quantitative measure of sunspots is sunspot number, which is a daily measurement of sunspots. Note, however, that sunspot number isn't simply a count of the number of sunspots. It also takes into account additional factors like the size and grouping of sunspots. Sunspot number is recorded by a number of solar observatories around the world, and sunspot number values range from 0 to a maximum recorded value of about 250. As mentioned a moment ago, more sunspots, or a higher sunspot number, almost always means better HF propagation. It's also worth noting that sunspot data have been collected for almost 400 years, giving us valuable information on how the number of sunspots changes over time. And sunspot numbers do change over time. In fact, sunspot activity follows a roughly 11-year solar or sunspot cycle, as shown in this graph. Generally speaking, sunspot numbers are usually around 150 at the peak of a cycle, during which time HF propagation is very good on most frequencies, including higher frequencies. At the bottom or trough of the sunspot cycle, sunspot numbers close to 0, meaning much poorer HF propagation. Given the period of the sunspot cycle, it should be clear that sunspot cycle is only good for predicting long-term HF propagation, that is, in terms of years, and over this time period it is fairly reliable. It's also, however, worth noting that at several points in history, for example in the late 1600s and the early 1800s, sunspot numbers stayed low for several decades, creating so-called minimums or minima with very little solar activity. The reasons for these minima are still very much a mystery. We can also quantify solar activity by measuring the level of solar noise, or flux, at a frequency of 2800 MHz. These measurements are reported as the solar flux index, with values given in so-called solar flux units. Measured solar flux values generally fall in the range of about 50 during a solar cycle minimum to about 300 during a solar cycle maximum. Since solar flux is a measurement, not an observation, it tends to be more consistent and reliable than sunspot number, but it also doesn't have the same 400-year history of values. However, solar flux values tend to correlate quite well with sunspot numbers. Like sunspot number, higher values of solar flux mean higher maximum usable frequencies and better HF propagation. Sunspot number and solar flux index are valuable measures of longer-term variations in solar radiation. The ionosphere is also affected by shorter duration events occurring on the Sun. The most important of these are solar flares, which are a type of eruption on the surface of the Sun. Solar flares cause a rapid rise in both X-ray and ultraviolet radiation, as well as the ejection of both low and high-energy particles. Solar flares are essentially unpredictable, but they do occur more commonly during peaks in the 11-year sunspot cycle. Solar flares have a significant effect on HF propagation because they can lead to sudden ionospheric disturbances, polar cap absorption, as well as both geomagnetic and ionospheric storms. As the name implies, a sudden ionospheric disturbance is sudden. It occurs about 8.5 minutes after a flare, that is, at the same time the flare becomes visibly detectable on the Earth, and is caused by the arrival of solar radiation. This radiation causes delayer ionization, and hence delayer absorption, to increase rapidly, starting at the lower frequencies and moving upwards. The affected frequencies are often almost completely blacked out. Fortunately, a sudden ionospheric disturbance only impacts the sunlit hemisphere, and tends to last a relatively short time, typically an hour or so. And in some cases, smaller solar flares can actually enhance HF propagation by increasing ionization at higher frequencies without a corresponding increase in delayer absorption. The next effect of a solar flare is something called polar cap absorption. The high-energy particles emitted by a flare reach the Earth several hours later, and the Earth's magnetic field prevents them from entering except at the poles. When they enter the atmosphere, these particles can increase delayer absorption in the polar regions, and this effect can last for several days. During this time, HF signals traveling through or near the poles will be blocked by this increased attenuation, but paths that do not go near the poles may remain relatively unaffected during this event. Geomagnetic storms are caused by lower energy particles arriving at the Earth. This occurs 20 to 40 hours after a solar flare. These particles can also be generated during something called a coronal mass ejection, which can occur independently of a solar flare. In either case, these particles can cause geomagnetic storms. Geomagnetic storms produce visible aurora, but they also can interfere with GPS signals, satellites in general, terrestrial power distribution networks, etc. Geomagnetic storms don't directly interfere with HF propagation, but they can create ionospheric storms. Ionospheric storms lower the maximum usable frequency and degrade HF propagation. And as mentioned earlier, if the MUF becomes higher than the LUF, an ionospheric storm can create a complete HF skywave blackout. One final note. It's possible to have a geomagnetic storm without an ionospheric storm, but the converse is not true. All ionospheric storms start out as geomagnetic storms. Sunspot number and solar flux index can be used to quantify ionospheric conditions, but to quantify geomagnetic conditions we use A and K indices. In general, lower values for A and K mean a more stable ionosphere, although, as we just mentioned, in some cases a geomagnetic storm may not lead to an ionospheric storm. A and K are measured at observatories around the planet, and these local values can be averaged to produce planetary values. One of the biggest differences between these two indices is that A is calculated daily, whereas K is measured every 3 hours. Higher values of K indicate a current or ongoing geomagnetic event, whereas A is useful in knowing how long this disturbance has been occurring. Let's summarize what we've learned. Global HF communications are usually based on skywave propagation rather than on direct line of sight or ground wave propagation. In skywave, signals are refracted by the ionosphere, although the effect of some layers is more to absorb signals than to refract them. Whether or not a signal is refracted or absorbed by the ionosphere is largely a function of 3 things: the frequency of the signal, the incident angle, and the amount of ionization in the upper atmosphere. Generally speaking, this ionization increases during daylight hours while the sun is illuminating that side of the Earth. On a longer time scale, ionization also increases as the number of sunspots increases, the number of sunspots following a roughly 11-year solar cycle. Aside from these semi-regular effects, certain types of solar events can unexpectedly or unpredictably disrupt the ionosphere and hence HF propagation. Solar flares are the most common of these, and flares can lead to so-called sudden ionospheric disturbances, polar cap absorption, and both geomagnetic and ionospheric storms. Coronal mass ejections are less common, but often a more severe, source of geomagnetic storms. And finally, we can quantify the current state of the ionosphere and/or make predictions about HF propagation based on measurements such as sunspot number, solar flux index, and the A and K magnetic indices. This concludes our presentation, Understanding HF Propagation. Thanks for watching.
Did everybody enjoy that?
Yes,
Pretty
it just
sure.
went really quick.
Yes, very good. It was fast though.
Yes, it was very fast. But yes.
Well, it covered a lot of material.
And that'll be out there for us to rewatch.
Yes.
It'll be in your it'll be in your stuff that we can access to watch it again. The link to the movie.
I'll send it, but it should be on the slides that are on Dropbox
And
also.
Yeah, right. That's what I was thinking.
Okay. Let me see if I can get back to where we were. Okay, we're still recording. Okay. So, like it mentioned, the sunspot cycle is approximately 11 years. They've been counting them now for, this is the 25th cycle. We're actually about 2 years past the peak. So we're starting to have degraded propagation.
I'm sorry, you said the sunspot cycle is 20 years?
I think I said 11.
Oh, 11. 11. Okay, thank you.
Approximately.
Super, thank you.
And like the movie said, the more sunspots, the better as far as propagation is concerned. There's some years or some cycles, let's say, that have a very low number of sunspots, and even at the peak, propagation is not very good. This current cycle, 25, is fairly good compared to some previous years. Not quite as good as cycle 23, but much better than 24. I don't have any idea what's going to happen in cycle 25. I might not even be here. This some data I went back and got. So cycle 23, which started back in August of 96 and ended in December 2008, had a peak in November of 2001, approximately the middle, of 180 sunspots. The next cycle, following from December 8th to December 2019, peaked at 81.8, like half. The current cycle, which started in 2019, goes to approximately 2030. They don't know which month, but the peak was in October of 2024. So we're looking at approximately 2 years ago, and it was only 160. It's still a good number, but not as good as what you saw in cycle 23. And if you go back, you can look up more information on the cycles and see how they varied. And this is an animation showing a big solar disturbance and how it affects the geomagnetic field of the Earth. And you see it finally ends up in creating what we call auroras, where it interacts with the Earth's magnetic field. Some of the things that they talked about on the movie was the solar flux, and it's measured in various things. This is more detail than you really need, but they measure the X-ray flux, the proton flux, which are actual particles, geomagnetic activity, which in this one it's showing the K planetary index, which is a number from 1 through 9. And over on the right-hand side is how they classify geomagnetic activity in G0 through G5, where G0 is kind of normal, typical, it's not causing any problems. So when you start getting up in, it's kind of a nonlinear thing. The 1, 2, and up through 5 layers, it becomes more and more of a problem. Like G5 would essentially wipe out communications. So the solar flux index they talked about is one of the measures, and they do it at a particular frequency, which is a 10.7 centimeter wavelength. I think it's 2800 megahertz, if I recall. And they measure that in solar flux units. They vary from something like as low as 60 up to around 300. And they kind of vary along with the sunspot number. So the higher the sunspot activity, the higher the solar flux index is. And essentially that means better propagation the higher those numbers are. It talked about the A and the K index. And the K index is one where they measure that every 3 hours at various places around the planet. And they average those 3-hour measurements, and it becomes the KP, and the planetary index, where the A index is sort of an average of the K indices, but it's not a direct average. They actually will convert the K indices back to actual solar flux units and add those up, divide by 8, and come up with the planetary A index average. So the K indices are kind of showing you real time what's going on every 3 hours. The A is intended to be like a more long-term look at it. And also the higher the sunspots and the solar flux, the more energized is the D layer, because you've got more ultraviolet and some of the other X-rays and things making it down into the D layer region and activating it, and causing it to be more absorptive for lower frequencies. It also generates more noise because there's more activity with the particles and molecules, which is why the D layer is pretty much useless for communications during the daytime. There's lots of sources out there where you can go look at a lot of this data. This happens to be one that publishes it sort of real time. And they list most of these things. If, you go to a site like this and you can find out what the current solar flux index is, number of solar flares, the A and the K indices, the X-ray flux and the proton flux and the electron flux. Those are all things being emitted by the sun, part of the solar wind. Information about the auroras, what the solar wind activity is, the magnetic field of the Earth, and the state of the geomagnetic activity. So it would be a G0 or essentially quiet. So the solar cycle really affects propagation, long range propagation, on some of the bands a lot more than others because of things we talked about. The lower frequencies get absorbed in the D layer during the daytime, uh, especially with higher solar activity. Turns out the 20-meter band is kind of in the middle, frequency wise, and it tends to be operational 24/7 and doesn't depend on the solar cycles as much. So even when we have a bad solar cycle or a null, which we're going into in between cycles, 20-meter band is still going to work for propagation. The higher frequencies, probably not. And that's what this one is. The typical 15, 12, and 10 that are used, and it also includes 6, which is VHF, become less reliable as we go into this null period, or just have periods of low solar activity. Okay, back to the sun. The surface of the sun rotates every 28 days. I never found anything that tells me what the core of the sun does, but they do know that the surface, since it's kind of a big ball of gas, rotates around what's inside. And therefore, any sunspots that appear on that surface are rotating away from the Earth. So when they're facing the Earth, you're seeing the activity being released through the sunspots. And as they rotate away, their effect is less and less. So you can see a change in solar activity every 28 days because of that, because you might have an area on the surface that has a lot of sunspots and other areas that don't. So you're going to see that increase and decrease as the sun rotates. And the biggest effect is going to be in the medium frequency, which is down below HF, and the HF bands, the 3 to 30 megahertz. It talked about ionic disturbances or sudden ionic disturbances, and they have the acronym SID. They always have to come up with a lot of acronyms. Being caused by large solar flares, like that little animation that we saw with that big solar flare and the stuff hitting the Earth's magnetic field. It causes a lot more ionization in the D region, which makes the D region even more absorptive. So frequencies down below 20 meters are going to be absorbed in the daytime even more when that happens. I think it also said it takes approximately 8 minutes, 8.5 minutes, and you can calculate it. The sun is 150 million kilometers from the Earth, so those waves travel at the speed of light. So it's approximately 8 minutes. If you have something like and we'll talk about a CME, a coronal mass ejection, where there's actually particles, neutrons and protons and stuff ejected out of the sun, other material. It doesn't travel at the speed of light, so it can take 20 to 40 hours to get here. If you have a big CME and it does get here, that's bad news. Fortunately, we've had very few documented cases over history where there's actually been a coronal mass ejection that hit the Earth. It would be potentially catastrophic. One of the saving factors is because the sun's rotating, and it takes 20 to 40 hours. The sun would have to be in a particular spot where it's not really pointing at us yet for that material to get here. So it's a hard shot to make, and hopefully it doesn't happen. They usually miss us. Those corona holes are those cool regions. Like he said, it was only, what, 3,000 Kelvin instead of 6,000? That's not very cold, but it's a big change. And I don't know exactly how that works, but it does allow magnetic fields to extend through those holes. And that produces more solar wind than you normally have the quiescent. So that tends to have a lot of effect on things. Not as much as the mass ejection, where, like I said, you get all these particles, plasma. I guess in some cases, depending on what stage the sun is in and making material, whatever the latest stage in that process is, something between hydrogen and iron is also going to be part of that material. Now, in this one, it says those CMEs can take as little as 15 hours to get here. Depends on the velocity, or up to several days. And it can really disturb radio communications. You can kind of think of it having a, if you actually had one, a giant EMP burst. So it would take out the power grid, things like that. Take out your cell phone, take out your computer. Geomagnetic storms are what we call, when we have a disturbance on the Earth's magnetosphere due to reaction from the sun. And one of the bigger effects is on the F2 layer. That's the highest layer in the ionosphere. Makes it very unstable. Like in that little animation, it created or accentuated the northern and southern auroras. You really always have an aurora, but they vary quite a bit depending on the activity. When the auroras are active, you can actually use those to reflect VHF signals, like 2 meter, 6 meter. And it's actually reflection as opposed to refraction. And because of that activity, it also degrades those high latitude propagations, because it affects the high latitude more than it does the middle latitude. I guess because the magnetic field is stronger at the poles. So all that's kind of associated if you have a coronal mass ejection, because even if we don't have a direct hit, sometimes we see the effect of it because it can be a pretty broad blast coming out of the sun. It will show up in the K index and also the A index. This is just another animation of, that hitting the Earth and how the solar wind part of it is perturbing the magnetic field of the Earth, where it should normally, be this symmetric flux lines, but that tends to disturb it quite a bit. We talked about the solar flux index, and there's the actual definition of what a solar flux unit actually is. It's like 10 to the minus 2 watts per square meter per hertz. So they call it a measure of the diffuse non-radiative coronal plasma heating. Not sure I really understand what that means. I've never looked it up. But it's just a measure of the activity that's useful. Like we said, the K index is called the short-term stability index, as opposed to the A, which is the long-term. And they measure the K index by taking measurements every 3 hours. And the A index is a way of averaging information from the K index measurements. It's not a direct average of the K index. Any questions on those? You don't have to remember all of this, just the salient features. Here's a little chart showing the relationship between the solar flux index, the A index, and the K index, and how they designate the different values. So you can see for the A index, A0 through 7 is very quiet activity of the magnetic field. And remember, the A and the K are measuring the magnetic activity. And the K index of 0 is essentially inactive. Up to a 2 is still quiet, kind of like an A0. As you start getting up into the 5 and above, that's indicating some form of a minor to an extremely severe storm. K9 would be an extremely severe storm. And therefore, you'd wind up seeing an A index, if that K9 lasted very long, of a very high A index. So, any questions on those before we do questions? Okay. So how does a higher sunspot number affect HF propagation?
Good propagation A.
Anybody else?
Alpha.
Alpha. Very good. What effect does a sudden ionospheric disturbance have on the daytime ionospheric propagation?
Bravo.
Bravo.
Bravo. Bravo. Yeah.
Very good. Approximately how long does it take the increased ultraviolet and X-ray radiation from a solar flare to affect radio propagation on Earth?
Is it
Charlie.
Charlie? Yeah.
Charlie.
Charlie. If you calculate it, it should be 8.33 minutes.
Take us 8.33 minutes to figure it out.
Yeah. That's true. That's true.
Which of the following are least reliable for long distance communications during periods of low solar activity?
Delta.
Delta
Delta.
doesn't have anything to do with low solar activity, does it?
Uh,
I mean, it's just is.
I thought it was low solar was the higher ones, and the high solar is the lower ones, right?
But low solar activity
the
makes
higher,
15, 12, and 10 better.
right.
Right.
The higher frequencies above 20,
Right.
okay,
It's so slow.
The question was, does during periods of low solar activity affect the answer?
Yeah, these are they're least reliable when you have low solar activity. In other words, it requires high solar activity, 15, 12, and 10 meters and 6 meters to be effective.
Okay.
So when
I'm
you
glad-
don't have a lot of solar activity, they don't work very well.
That's what I was remembering, but I thought it was always
Yeah.
true for
Right.
long distance communication. So that's a good correction. Thank you.
And they also don't work as well at night because you have less solar activity.
Right.
The F layer shrinks into a single F layer, and it's not as thick. It doesn't refract as much. So what is the solar flux index?
That's at 10.7. 10.7. So it's delta.
Yeah, that's a good one to remember, that 10.7.
Yeah.
What is a geomagnetic storm?
Delta.
Delta.
At what point in the solar cycle does the 20-meter band usually support worldwide propagation during daylight hours?
Delta.
Delta.
20, because 20 you said is always good.
20 is always works, not necessarily always good.
Well, yeah. Okay.
How can a geomagnetic storm affect HF propagation?
Delta. Degrades the high latitude HF propagation.
You're paying attention.
Whoa, I'm getting lucky is what I'm getting.
Yeah.
How can high geomagnetic activity benefit radio communications?
Alpha?
Alpha, you.
Yeah, because of the auroras. Yeah.
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 The others are sort of red herrings. What causes HF propagation conditions to vary periodically in a 26 to 28 day cycle?
Charlie.
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 Yeah. When it's said a 28, it rotates 28 days approximately.
Mm-hmm.
Apparently, it's not consistent. I don't know. Maybe the sun wobbles.
Mm-hmm.
How long does it take a coronal mass ejection to affect radio propagation on Earth?
I thought the slide said 20 to 40 hours to reach Earth. So, I mean, the only closest thing is Delta.
Yeah, well, it also, one of the slides said 15 to several days too.
Oh, okay, well, I need to
Okay.
encourage my notes.
Yeah, I was trying so hard to take notes, but it was going so fast.
Yeah, it was.
All right. 15 to several days. Coronal mass.
What does the K index measure?
Oh, K is hourly. Wait.
Short term, so it's
Sure.
short term ones.
Right.
So Bravo,
Right. 3 hour measurements.
3 hour measurements.
What does the A index measure?
The long term.
Charlie.
Yeah, it's Charlie.
Charlie.
Sort of the daily average.
Right.
How is long distance radio communication usually affected by the charged particles that reach Earth from solar coronal holes?
Bravo.
Alpha.
Mm,
No.
It's disturbed.
long distance radio. That would be
Well, is it one of the VHF, UHF ones?
I was gonna say Delta.
Have we talked about ducting?
I
No.
don't know. It doesn't sound familiar.
Well, then you probably erase those two.
I want to
it
say
Delta?
alpha. Does somebody want to say Bravo and I'll say alpha?
Yeah.
And one of you will be right.
Oh, okay.
There you go.
Now that's long distance radio. So long distance radio isn't used on VH and UH.
Uh, Typically, VHF and UHF, you don't get the kind of propagation that you do with HF. So
Okay.
you don't get long distance communications.
Okay. So I'm just trying to figure out how to use the word question and the answers and find something that I can connect them to. So long distance and HF communications.
Yeah, long
Disturbed.
distance, you usually associate that with HF.
Got it. And it's disturbed. All right.
Yes. Okay.
Stop recording.
Yes. She's good.